In the depths of space, among the cold and ancient interstellar voids, remarkable wanderers traverse distances beyond human comprehension. Every so often, these cosmic voyagers reveal themselves with a flash of unexpected light in the night sky or a mysterious path through our solar system. Most recently, one such emissary from the space between stars, 3I/Atlas, was discovered streaking through our neighborhood in the summer of 2025. This breathtaking find wasn't merely a curiosity, it opened a tantalizing window onto some of the most profound mysteries about how worlds are born around distant suns. Imagine, objects like 3I/Atlas, forged in the crucibles of foreign solar systems, ejected into the galactic wild, may carry within their rocky and icy forms the potential to spark new planetary systems wherever they wander. Our story tonight begins not only with the detection of this third known interstellar visitor, preceded by 1I/Oumuamua and 2I/Borisov, but with a bold new theory presented by Professor Susanne Palsner of Forschungszentrum Jülich in Germany. At the 2025 EPSC-DPS joint meeting in Helsinki, Palsner unveiled research suggesting that the very fabric of planetary birth may be intricately tied to these interstellar nomads. Her findings, delivered to an audience of scientists whose life work is unraveling the secrets of the cosmos, challenge and expand our understanding of how planets, especially giant worlds like Jupiter, are able to emerge from the swirling disks of gas and dust that cocoon infant stars. For decades, astronomers have gazed with wonder at protoplanetary disks, immense spinning halos of particulate matter that accompany the earliest days of stellar evolution. Within these disks, trillions of dust grains are thought to collide, stick, and gather into ever larger aggregates, ultimately forging entire planetary systems. But the process, elegant on paper, has always concealed a profound puzzle. Computer simulations, full of particle physics and celestial mechanics, repeatedly show that as dust grows into rocks and rocks into boulders, a destructive barrier appears. Instead of gently coalescing, meter-sized chunks tend to bounce away from each other, or worse, shatter altogether. The dream of assembling a planet from scratch, pebble by pebble, seems to stumble at this crucial threshold. Here, in a stroke of cosmic ingenuity, enter the interstellar objects, like 3I/Atlas, castaways from other star systems, traversing the interstellar wilderness. These objects are theorized to be the solid relics of primordial chaos, perhaps ejected during their home system's own planet formation struggles. Now, as they traverse the galaxy, drifting through the infinite night, a rare but powerful opportunity arises. When a young star's planet-forming disk sweeps through space, it doesn't exist in isolation. It swims through a sea peppered with interstellar wanderers. According to Professor Palsner's models, each protoplanetary disk has the gravitational strength to snare millions of these interstellar objects, solid bodies comparable in size to the remarkable 1I/Oumuamua, which itself measured roughly 100 meters in length. Picture this, a disk, radiant with heat and the light of a new star, quietly gathering up not only its own stardust, but also ready-made messengers from distant worlds. These cosmic stowaways could become the very seeds from which entirely new planets grow.
The ramifications of such a process ripple out in every direction. For interstellar objects, their journey, once begun as a random trajectory through the darkness, could ultimately end as the core of a future world. For the disk itself, the presence of these sizable, stable seeds could bridge the daunting size gap that has challenged our planetary formation models for so long. But there's more to this elegant solution than merely solving the case of the meter-sized rock. This mechanism holds the key to another enigma that has captivated planet hunters: the origin of gas giants like Jupiter, especially around stars more massive than our own Sun. Astronomers know that the immense gaseous worlds detected by our telescopes and space probes are far less common around the smallest and coolest stars, the so-called M-dwarfs, where such giants are exceedingly rare. Instead, gas giants are routinely found orbiting stars that resemble or exceed the mass of the Sun. Yet, combining all we know about the short-lived and turbulent environment of a protoplanetary disk, where the raw materials for planetary construction are blown away after only about 2 million years, it seems nearly impossible for such giants to form quickly enough by standard models. The clock runs out before the process can reach completion. Palsner's models suggest a breathtaking solution. If a protoplanetary disk, especially one surrounding a more massive star, can efficiently capture millions of interstellar objects as seeds, the very timeline of planet birth accelerates dramatically. These objects are not subject to the same fragile, fragmentary beginnings as locally formed rocks. With the sudden presence of these seed cores, material accretion can proceed at a far swifter pace, fast enough to allow gas giant planets to fully form within the fleeting lifespan of the disk. Suddenly, the prevalence of magnificent Jupiter-like worlds around higher-mass stars is not only explained, it's expected. Professor Palsner distilled the marvel and significance of this hypothesis. Interstellar objects may be able to jumpstart planet formation, in particular around higher-mass stars. The efficiency with which these larger, more massive disks can ensnare interstellar objects means that planet formation sparked by cosmic visitors should be especially common and rapid around such stars. And, as she emphasized, their fast formation is exactly what we have observed. The very existence of colossal gas planets encircling bright, sun-like stars appears to bear witness to the hidden journeys of objects like 3I ATLS, messengers not just between stars, but between generations of worlds. But this cosmic story is far from finished. The discovery and the models it inspired ignite a host of new questions, each as mesmerizing as the last. How evenly are these interstellar objects scattered when they are captured? Are they distributed uniformly across the swirling plane of the disk, or do gravitational eddies and streams gather them into dense clumps, potential crucibles for planetary birth? How many of the millions of captured interstellar objects ultimately go on to form planetary bodies? Could there be regions within the disk, perhaps mysterious planetary nurseries, where the seeds of future worlds are formed at a fevered pace? It is staggering to imagine the scale of what Professor Palsner describes. Each disk, countless billions throughout our galaxy, becoming a gravitational net, catching the wandering relics of other stars. Space itself, charged with the task not just of dispersal, but of eternal renewal. In this grand vision, our own solar system may bear within it not only the echo of the star that forged it, but the memory of worlds long vanished, preserved in the seed of a giant planet or the core of a wandering comet. With every new detection of an interstellar object, be it Oumuamua, Borisov, or the luminous 3I ATLS imaged by the Hubble Space Telescope, we are reminded of how porous the boundaries between planetary systems can be. Stars do not merely scatter rocks upon the tides of the galaxy. Those rocks can, in the fullness of time, return to build new worlds, perhaps stranger and grander than their birthplaces could ever have imagined. As Professor Palsner's research moves forward, she and her colleagues will tune their simulations, seeking to measure precisely the success rate of these cosmic seeds, how the ballet of gravity, motion, and chance crafts the beginnings of future planets. Will statistics bear out that higher-mass stars, with their deep, hungry disks, truly are galactic pioneers, capturing more interstellar objects and giving rise to more giants in less time? Or will new mysteries appear, layered atop the old, driving our curiosity even further as we chase the processes that shape the universe's planetary tapestry? This vision of interstellar objects forming the backbone of planetary formation, especially around the galaxy's blazing young stars, is a humbling reminder of how interconnected our cosmos is. Material ejected in one violent episode of planet formation may sail for millions, even billions of years before finding another home, another chance at becoming part of a world. It is a cosmic dance, endlessly renewed, a story written not just in the orbits of planets, but in the infinitesimal histories of every particle, every rock that drifts through the vast and silent dark.
Here, under the light of distant suns on the shores of star-forming clouds, the seeds of new worlds are sown, not only by local circumstance, but by the ancient and far-flung journeys of celestial travelers like 3I ATLS. Their crossings remind us that every world, our own included, may bear the imprint not only of its own making, but of the cosmic neighborhood in which it arose, a neighborhood alive with sharing, with movement, with the boundless promise of the galactic sea. As we look up, inspired and awestruck by these discoveries, we are called to remember, the universe is not a static tableau, nor are its systems closed, sealed, and solitary. Instead, It is a dynamic, breathing expanse where the lines between past and future, here and elsewhere, blur and dissolve. The next time you gaze into the night, ponder that our solar system, planet Earth, the Sun, and likely even the giants of our planetary family may carry echoes of other stars, whispered across eons and handed down in the form of ancient interstellar visitors. With every step forward, with every new finding, like Professor Pultzner's evocative work, we deepen our understanding of what it means to share a universe so rich with possibility. Through the lens of science, our awe multiplies. We see anew the wonder in the ordinary and glimpse the extraordinary in the silent journeys of objects across interstellar space. So let us carry this sense of curiosity and amazement with us. The universe is ripe with stories yet to be told. Stories of origins, pathways, migrations, and connections. We stand just at the beginning. As we await the next great visitor, and as models like these help illuminate how worlds are spun from the cosmos itself, let us continue onward, ever exploring, ever learning, ever in awe of the boundless frontier. Stay with us as we journey together through these mysteries, led by research, discovery, and an enduring fascination with the stars. The story of 3i ATLS and the seeds of worlds yet to be is only one chapter in an endless, majestic saga, a saga that invites us all to become explorers of the cosmos.